So let's start. Any comments, questions before we get to the material? So let's see. Okay, so did you guys get a chance to go over the material? The lecture
material?
video? I mean, the lecture videos, did you go over the maximum likelihood?
Yeah, last time Professor asked us to go over geometric interpretation.
Yeah.
Which was lecture 9, yeah.
Yeah, and then I also asked you to go over the details of the MLE. So if you haven't, okay, so I went to, okay. Yeah, the lecture, I'm going to focus on the lecture on the geometric interpretation, but it's worth also just going over the derivation, the MLE that we sort of did briefly in class. I'm hoping that you go over this in the videos for yourselves, and if you have questions, ask me, or here in the lectures or in the office hours or from the TA. Okay, anyway, so you went over the geometric interpretation. We talked about this last lecture. So any questions or comments about this? Is it clear to people?
Yeah, I just have a little question actually, Professor.
Okay, good, go ahead.
It's regarding the proof that LMX thing and kernel X transpose.
Are you talking about this slide, or is it one of the slides?
Yeah, I think it's before, right here, yeah. It says to prove that the LMX thing is the kernel. It's aligned by orthogonality principle.
Oh, yeah, okay.
And are you expecting us to prove this, to know this, kind of just know the principle behind this? Or I'm just wondering if we can go over a little bit over that part.
You mean this part? The one that follows this?
Yeah.
Mm-hmm. Yeah, okay. So we actually did go over this part last time. So this is the geometric condition for the projection. So if mu hat is the projection, so let me remind you what this setup was. So we reduced the least squares problem, which is finding the beta, the coefficient vector of regression. So we reduce the MLE to the least squares problem, and the least squares problem can be written in this rather abstract way, which says that given y, what is the closest mu in the image of x to y? And this is a projection problem. And the solution mu hat would be the projection of y onto, so if this is y, we project it onto the image, and then we get mu hat. So mu hat would be the solution of this problem. And so geometrically, we see that, or you can argue that this projection is characterized by the fact that this residual vector, y minus mu hat, is orthogonal to the image of x, which is the subspace. So what this means is that anything, if I pick any vector in this subspace, this error is going to be orthogonal to it. So that's, if you recall, the meaning of this notation, that E is orthogonal to the image of X. So there are multiple ways of arriving at the next conclusion, but the easiest way is So we went through one version last time. Another way is to see that, so this is one way. I'm going to do another way. So we saw, or last time, that E being orthogonal to the image of X is equivalent to X transpose Y minus mu hat is equal to 0. And this is X beta hat, basically. So this we did using a certain approach. Now I'm going to do another way, just to see that there are many ways. Another approach to show this. So this is the residual. You can verify. So we want to show that E is in the image of X if and only if X transpose E is 0. Okay, so that's basically this. This is E. And this is saying E is in the image. E is orthogonal to the image. Then this is saying that X transpose E is 0. So if I write X, so proof, if I write X as X1 dot 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 XP plus 1, let's say. No, actually, let me do it. X0. So these are the columns. X1, XP. So these are the columns up. X0, X1 up to XP are the columns of X. So argue that E is orthogonal to the image if and only if E is orthogonal to Xj for J, 0, 1, 2, for all these columns. So it's enough, necessary and sufficient that E is orthogonal to all these columns. In this statement, this is equivalent to basically Xj transpose E is equal to 0 for J equal to 1 to 0, 1 up to P. And this in itself is equivalent, or this is equivalent to X transpose E is equal to 0, because X transpose has these as rows. So X1, 0 transpose, X1 transpose, XP transpose. So this verify for yourself that these are equivalent. So this is equivalent to that, and this is equivalent to this. So we have proved this, that E is orthogonal to the image if and only if X transpose E is 0. Now, what does this, what is an equivalent way of stating this in terms of the kernel and image of X transpose? Is this relation
Is it
related?
that E is the kernel of X transpose?
E is in the kernel. It's not the kernel itself, but it belongs to the kernel, because that's the definition. So vectors are in the kernel of X transpose if X transpose E is or x transpose times that vector is 0. And so this is just exactly saying that. So you have shown, and this argument doesn't have anything to do with what E was. So we showed that E is like orthogonal to the image if and only if we can write this. So E belongs to the kernel of X transpose. So this shows that in fact image of X perp is equal to the kernel of X transpose, because image of X perp is the set of all vectors that are orthogonal to the image. And these are exactly the vectors that are in the kernel of X transpose. So this argument actually proves that statement. You're not required to be able to do this, but you can see it's not that difficult. It's just useful to learn. And you can use this. Now, if you agree with this, then this you can see that this is just nothing but this. So the idea is that if you remember this, you can just write down this expression immediately. So this is E. And this is saying X transpose. E is 0. If you don't remember this, you can just drive it. This is like the derivation. We did it another way last time, and we arrived at the same conclusion. And then once you have this, you replace mu hat with x beta hat, and you get these normal equations. Okay, does that make sense, or makes it more clear?
Yes, thank you.
Yes, okay, no problem. Any other questions, comments? No questions? Okay. So this is a good way of viewing linear regression, and there are a lot of consequences to it. So to recap, so what we do, let's say in linear regression, at least if you want to find the least of squares estimate, which is the common estimate, is that you project the observation vector, or vector of observations y, onto the image of x to get the mu hat. So this mu hat has a name. Anyone knows what the name of this is? Or the entries are? In the context of
Is that
go ahead.
Is that hat matrix, mu hat?
So it's a vector. It's related to the hat matrix, which we'll see. But it itself is not like technically it is a matrix, but it's like a n by 1. It's a vector. So it has entries. The entries are the fitted values. So if you go back to your previous courses, this contains the so-called fitted values, right? So when you fit a regression, you would have a bunch of points, and yes, your fitted values would be the values of the like the line that you fit associated with these points. So those are those fitted values.
So like the y hat, right?
Yes, it's y hat actually. Some people write it as y hat. I'm writing it as mu hat, and your book also does it as mu hat. Yeah, it's the same thing, just different notation. So we form this, and once you have these fitted values, then you can also get beta hat. Basically, you can solve this linear equation. It's like a linear system of equations, and you find beta hat. Or you can just write this down, and you can see that it's beta hat comes out as the usual formula. So one point to point out, which is a good place to point out, is that this projection, these vector fitted values, is always unique in general. But beta hat need not be unique. It's only unique if X has full column rank. So the projection is always going to be unique, but the beta hat, which is how you write this mu hat as a linear combination of the columns of X. So if you remember, this can be written as this. So xj's are the columns of x. So this representation might not be unique. So you might be able to write this in using different combinations of x's. So you can write mu hat as two different linear combinations, for example. If the column rank is not, if the matrix is not full, does not have full column rank, because some of the x's you can write the columns as linear combinations of the others, and you can see that this translates to having multiple possible ways you can write this as the linear combination of the columns. But geometrically, you can argue for yourself that the mu hat has to be unique, and because you're making this assumption, the beta hat is also going to be unique. Okay. Questions? Okay, so.
Sorry, Professor.
Yeah.
Do you mind explaining one more time that the reason why beta hat doesn't have to be unique? You said because it's a linear combination, right?
No, what I said is that, so in general, mu hat, because mu hat is in the image, mu hat can be written as a linear combination of the columns of x, right? Mu hat can be written like this, or equivalent to that like this, which is a linear combination of the columns. So x being full rank means these, so these are the columns of x. So these columns, these sets of set of these vectors, is either linearly independent or linearly dependent. Okay, so if they're linearly independent, then so argue that if x0, x1 up to xp are linearly independent, then if I have j's, this beta hat j x j, let's say this combination, I can write it in two different ways. As I have this linear combination for mu hat, and it turns out to be this equal to, let's say, gamma j xj, then it follows that beta j is equal to gamma j for all j. This we can show from linear independence. And the other way is also true. So if they're linearly dependent, then there is another gamma j such that this whole. And then so you don't have a unique representation of mu hat as a linear combination of the columns. So different things could go here and give you the same mu hat. Okay.
Okay, that makes sense. Thank you. So that's the multi-collinearity that you talked about last time.
Yes, that would be multicollinearity. Yeah. So this is the opposite of multicollinearity. So the opposite, yeah, is that they're linearly dependent, and this is also equivalent to the rank condition. So they're linearly dependent. So this is equivalent to x being full rank. And opposite of multicollinearity. That's great to point out. Multicollinearity. Yeah. Okay. Any other questions? Okay. So a couple of more. So this vector E is the usual residual. So this is the difference between y and mu hat. This vector is basically the projection error, the error that you incur in projecting y onto mu hat, and that in the statistics is called the residual vector, and has these two expressions. Mu hat, as I mentioned, contains the fitted values, sometimes referred to as y hat, as Danny pointed out. And there are some consequences of this geometric interpretation now. So one is that, so this condition, if you remember, was the key. So this was the key geometric insight that we had. And then this led to the geometric derivation of the normal equations and so on. And so this geometric interpretation is very helpful because it has some consequences. So this is saying E is going to be orthogonal to anything in the image. And in particular, any column of X, so if Xj is the jth column of X, any column of X is in the image by definition. So E is going to be orthogonal to all the columns of X, the design matrix. In particular, if you have included the intercept in the model, then you have included a vector of all ones in the design matrix. In that case, E is going to be orthogonal to the vector of all ones. So this is only true if your design matrix contains a vector of all ones, let's say in one of the columns, usually the first column. And if not, then this is not necessarily true. So this is going to be only true if you include an intercept in the model. And this is just another consequence of the fact that in that case, this is going to belong to the image because this is going to be one of the columns. And this being orthogonal to the vector of all ones means that E transpose 1, this is the vector of all ones. So 1n is just 1, 1, 1 up to all of them are ones. So this is n by 1. A vector that has all the elements equal to 1. And so if you expand this, you'd conclude that it's just the meaning is that the summation of all the entries is 0. So that's what you usually see. Let's say a first course in regression that the sum of the residuals is 0. And it's going to be only 0 if you have the intercept in the model. And now you have an understanding, a geometric understanding, because E is going to be orthogonal to anything in the image. And one of the things in this image is just the vector of all ones. And you have, and this is going to be orthogonal to that as well. Another one is like the first column. And the other one is like the second column, and so on. So it's going to be orthogonal to every one of these vectors.
Professor?
Yeah.
Regarding the vector of all ones, do you mind if I ask kind of a question regarding that in the homework here, or do you, is that okay?
No, yeah, go ahead.
So is there a way to simplify a matrix that says 1 transpose, like an n by n matrix times 1? So it's a vector of 1's transpose times an n by n matrix times a vector of 1. Is there a way of simplifying that, since
a vector of 1's?
1 transpose,
yes,
times a matrix, say H, like H is n by n, and times 1.
Okay, good. So this is n by n, this is n by 1 vector of all ones. Okay, so you want to simplify something like this?
Is it possible, or is that like a final answer?
I don't know. It depends what you're after. You can write down an expression for it. This is what is the dimension of this?
1 by 1, right? 1 by 1 dimension.
Yeah. This is yeah. So this is just a scalar. It's just 1 by 1, and you can write it as just it's just going to be the summation over all the entries. So you can verify that this is just summing all the entries of the matrix. Whether that's useful or not is a different story, but so in general, if you have, no problem, if you have like A transpose H, B, these are vectors, then you can write this as it's just going to be a weighted combination of the elements of J, with the weights being AI, Bj, or all I and J, basically. Okay. Any other questions? So yeah, I was finishing this. So another vector in this is like mu hat. Mu hat itself is in the image. So E has to be orthogonal to the mu hat as well. So that's another consequence. Sorry. Oh. Okay, fine. Let's see if I can fix this. So yeah, so another vector is mu hat, and so we get let me take this out. Complete this. Okay. Yes, another consequence is that E is orthogonal to the mu hat. So this is, again, can expand it, it would be like that. So these are useful as, let's say, diagnostics. So you could, let's say, if you have fitted the linear regression, you can verify that these hold to make sure that you actually did the fit correctly. And they don't have anything to do with what the model is correct or not. These are going to be always the case, or always true, if you fit it to find the least squares estimate, no matter what y and x are. So this is just the consequence of the way that you fitted the model, which is just a consequence of the projection operation. So you don't need any assumptions for these to hold, besides the fact that this residual is coming from the least squares estimate. So this has to be the least squares estimate. Okay. Yeah, so that's mostly this slide. And there's this extra notation that we sometimes write. So your book has this, let me do it here. So there was this notation in your book that S beta is norm y minus x beta squared. This appeared in the exponent of the PDF. And so so we minimize this. So you minimize this over beta, and because the minimum that's the least squares estimate, the procedure for finding the least squares estimate, and the minimum is just beta hat. So this is just going to be the E squared. Okay, that's one last piece of information which is useful. Okay, questions? Okay, if not, I'm going to quickly go over this, and then you can go over these in the recorded lectures. So this concludes our discussion of the estimation of beta. Once we have this, we had the likelihood, so you can plug in beta hat, which is the optimal choice for beta, and then the likelihood, sorry, would simplify to this, and you can see this beta hat appears here, and this is just the residual squared. So now this is going to be only a function of sigma squared. So that's my sigma squared there. So I have the sigma squared. So once I fixed beta hat, then I'm only looking at a univariate function of sigma squared, and I can now solve this optimization problem. So I can find what is the sigma squared that maximizes this likelihood, and then you go through the procedure again. You can take the log of this likelihood, and then you can try to maximize it by taking the derivative and then verifying the second order conditions. And the end result is that you get that sigma hat squared is S beta hat over N, or just the residual sum of squares. So this is called residual sum of squares because this can be written as basically what the name suggests. So this can be written as the summation I from 1 to n ei squared. So this is the residual sum of squares, or some residual sum of squares, or sometimes called E. Yeah, you're forgetting about the name, so we'll talk about the name. There are different names for it. Okay, so yeah, so what I wanted to say is that the end result is that your estimate of sigma hat is going to be this residual sum squared divided by n. Okay. So that's the maximum likelihood estimator of the sigma, which comes out of the maximizing the likelihood. In practice, what would happen is we would replace this guy. We're not going to use this. We're instead going to replace the denominator with this number instead of n. And we'll see why we do that. So compared with the MLE, the only difference is that we replace this n with this. And we're going to use this as our estimate of sigma squared rather than the MLE. And the difference is going to be small when n is large. So when n is much larger than p, this is going to be approximately n compared to pn would be very large. For a small p, there would be a difference. The reason why we do this is that this S squared is going to be an unbiased estimator of sigma squared. So we'll see that later. Sigma hat itself is not unbiased. So anyone knows what unbiased means in this context? What does it mean to say that S squared is an unbiased estimate of sigma squared?
Is that just the expectation of the estimation is just a parameter itself?
Yes, exactly. So the expectation of S squared is going to be always sigma squared, no matter what value sigma squared actually takes. So for whatever value sigma squared, true sigma squared is, my expectation is always going to be equal to this. Okay, and that's what unbiased means. And we'll see that this holds. So this is useful. What this is saying is there's a frequentist interpretation of all these results. If I repeat the experiment many, many times and I form this estimate for each experiment, I form this estimate and then I average those estimates. That would give me an estimate, like an approximation of this expectation. That would be very close to the true sigma squared. So you can do it in R or some other programming language if you're interested. Generate from the linear regression model y and x. So use fixed y and x, and then you have a sigma squared, and you generate from that noisy model. You fit the model, you get the beta hat, and you get the squared. And you repeat the experiment many, many times, and then you take the average of your S squared, and the average will be very close to sigma squared. It has some interesting consequences later on. Okay, questions? Comments? So we're done with the estimation. If you have questions, let me know. One more piece is this hat matrix that came up, and you have seen in your homework. How many people have seen this? Have you seen the hat matrix before? I guess Danny should have seen it because he mentioned it. Other people have seen it? No, outside, not outside this class, okay?
Yeah, sorry, I've seen it.
Okay, so where did you see it? In a previous class or? Others haven't seen it, so was it in a stat class?
I mean, it probably means like homework 1 or
homework
2.
You've seen it in homework 1, okay. Yeah, so yes, okay, so you have seen it in the homework 1, probably homework 2, maybe homework 2, yeah. So this matrix that you can go back to your homework and see that all the stuff that you did was not irrelevant. So this matrix appears if you try, so this was beta hat. So now we know that mu hat is x beta hat. And so if I expand it, I get x transpose, x inverse, x transpose y. And so this is a matrix n by n, which is called the hat matrix. And what it does is that when you multiply h, so you take any vector, you multiply it by h, you get the projection of that vector onto, so this is the projection of y onto the image, and this hat matrix is an operator that produces that projection for you. So you take the vector y, and you want to find the projection onto the image. All you need to do is multiply y by h, and you get that vector. So this gives you a very simple like conceptual procedure. And the fact is that this does not depend on anything but x. So this is projecting onto the image of x. The only thing that you need to know to form this matrix is x, or its columns, or basically the image of x. And this is an explicit form that you can form that projection. This is also, we'll see, this is an example of projection operator. The better name for it in linear algebra is that it's an orthogonal projection matrix, or orthogonal projection operator, because its job is to take a vector and give you the projection of that vector onto the image. And in fact, you can also show that this matrix H has the same image as the X itself. So it's also projecting onto its own image in any case. So does that make sense? Is this clear? Where this comes from? Yeah, we showed that this is a projection of y onto, this is the projection of y onto the image of x, and so this matrix has to produce that projection, because we didn't assume anything about y. Any y that I plug in to the argument that we did should work, and this expression should give me the projection, and so this is the matrix that does that for any vector. And so some of the properties of this matrix, which is true for any projection matrix, is that it's a symmetric matrix. You have verified this in your homework problems. H transpose H is equal to H. It's idempotent, which means that H squared is equal to H. And it turns out that any vector, any matrix that has these two properties is an orthogonal projection matrix. So this is an if and only if. So necessary and sufficient condition for a matrix to be an orthogonal projection matrix is that it's symmetric and idempotent. And the fact that it's symmetric goes back to the orthogonality of the projection. It's a little bit tricky because there are also other type of projections you can project in an oblique fashion, which we're not going to talk about in this course. The idempotence just goes back to the fact that this is projection. So what this is saying, you can verify for yourself that this is saying that if I project the vector once onto the image, and then if I project this one again onto the image, I get back the same thing. So projecting twice doesn't change things. So you project once, you can change the vector, but once you project it, then projecting back again, because this is already in the image, it's not going to take an effect. So you can verify for yourself that this statement is actually equivalent to this, and this is just saying that this is my projection. If I project it again, which is multiplying by h, I get back the same thing, which is my original projection. So this is really a geometric property that the projection matrix has to have. And it turns out that I minus h also is a projection matrix. All you have to do to verify this is to verify that it's symmetric and idempotent, which you can do for yourself. And then the question now is that what is the space onto which this projects? And it turns out that this projects onto the image of x perp, the orthogonal complement of the image. So what happens, like the picture that you have to have in mind, is that every vector can be decomposed into two pieces. This we have seen very early on, if you go back to the projection discussion, into two pieces. One piece is the component in the image of x, and the other piece is the component in the orthogonal complement of the image. So E, remember E is orthogonal to the image of x. Another way of saying this is that E belongs to the image perf, or the orthogonal complement. So you're seeing this, and this can be compactly written as hy, this is mu hat, plus I minus hy, which is E. So this produces the component which is in the orthogonal complement, and this produces the component which is in the image. So if we do a little bit of discussion here, so this is the image, right? And the orthogonal complement of the image is, as you have seen before, this line. So I have the image and the orthogonal complement, and what I'm doing is I'm decomposing the vector into two pieces. One piece is along the image perp. The other piece is in the image image of X. So every vector can be written as the sum of these two pieces, and you can get these two pieces by multiplying by the corresponding projection matrices. Okay, so this is just an expansion of the discussion of projection. Now you have some context. For example, you can think of these components. This is the fitted values. This is the residual regression. So a very nice connection between the linear algebra concepts and linear regression concepts. And the matrices help you compute those projections. Okay, any questions about this? Good, okay. Everyone else, okay? Okay. So let's move on then. There is a piece about gram matrices which is useful to know. So this is like a side note. This matrix that appears in the middle, this guy is also has a name, X transpose X, and this is called the gram matrix. And if you write the columns of X, these are our usual notation. So these are the columns of X as X0, X1, X2 up to XP. Then you can show for yourself that the ijth entry of this X transpose X is Xi transpose Xj, or in other words, Xi inner product with Xj. So this so-called gram matrix contains all the pairwise inner products of the columns of X. So you get the P plus 1 by P plus 1 matrix, and it contains all the pairwise inner products. In particular, if the columns are pairwise orthogonal, then all these off-diagonal entries, so if this is for all not equal j, there's 0, that it means that you just have something on the diagonal. Diagonal is there, but then the off-diagonal entries are 0. Then it means that these vectors are pairwise orthogonal. So if your design has pairwise orthogonal columns, then this simplifies to a diagonal matrix. This is helpful. Yeah, go ahead. Do you have a question?
Just to double check. Yeah.
Okay.
In the middle of the page, it says that ij is from 0 to p plus 1.
Oh, okay.
Right.
Yeah, right. This has to be. You're right. This has to be p.
Okay. Yeah.
Yeah. Good. Okay, so that's the meaning of the gram matrix. So and it's useful to remember this property. So if I tell you that you have X and the columns are pairwise orthogonal, then you know something. If I tell you that, for example, all the columns are orthogonal to X0, which is usually 1, then you know something about the first row of this matrix. So if that's the case, then I know, for example, that this is first, the diagonals are going to be the just the norm squared. From this you can verify the diagonals are the norm squared of these vectors. And if I know that, for example, xj is orthogonal to x0 for all j from 1 to p, then I know that this first row is 0 because these are the inner products with that. The rest I don't know. If I have additional information, I would get that. But that's an example of how you can use this to have some quick calculations. And one last piece that you can show as an exercise is that these gram matrices, matrices that can be written as X transpose X, they're always positive semi-definite. So this is another useful piece of information. So anything that can be written as X transpose X is a gram matrix, and any gram matrix is positive semi-definite. And this follows, there's a little argument here, which I'm not going to go through. You can verify for yourself using the definition of positive semi-definiteness. Questions? Maybe one last piece is that the rank of the gram matrix is the same as the rank of the X that's generating it. So that helps us when we invert this. So we wanted to invert this at some point. And you assume that X is full rank, then it means that this is full rank. And because the square matrix, it's going to be invertible. Yeah, and there's a little argument there, optional argument if you want, that proves this. Okay, so I'm going to skip this. And questions? Any questions about this? Okay, so there's an example here in the slides that work out some of these expressions for the case where you have just one covariate. This is sometimes called simple linear regression. So you have an intercept, so your X matrix is going to have a column of all ones, and then one extra column, which corresponds to a single covariate. So your design would be n by 2, and then all these expressions can be written down, and some of them a little bit simplified. And if you go through it, you would see your usual expression that you might have seen for let's say the components. So beta has 2 entries, so beta hat 1, and beta hat 0, and beta hat 1. And you have these expressions which usually see in lower division courses. So I encourage you to go through it, and also there's some discussion in the lecture videos. So I'm not going to spend some time on it because this is a very special case. But everything that you want to know about this simple linear regression follows from their general discussion. Okay, so let me stop and see if everything is fine with people. Questions about this? So we're done with estimation, or at least derivation of the estimators. And we're now ready to move on to the next topic, which is studying the properties, statistical properties of these estimators. So maybe give you a few, let's pause 1 minute, think about whether you have any questions about any of this. And we'll come back and discuss this. Okay, 1 minute break and see if you guys think about whether you have any questions. Not, and then we'll come back. Okay. We're back. Any questions? Comments? Guys are there? No questions? Okay, so let's move on then. So we have the discussion. Like we're continuing the discussion of the linear regression, and we want to now study the properties of the estimators, beta hat and sigma hat squared. And the way we view the problem is that these are random quantities, and due to the randomness, basically due to the randomness in the epsilon, so remember y was x beta plus epsilon, so there is a true beta that's generating the y's, and then there's noise in the generation. And so these estimates are quantities that depend on y. So this, for example, is x transpose x inverse x transpose y. Hence, beta hat would be a random quantity itself. Similarly, for sigma hat squared. And so what we want to do is to characterize the distribution of these random variables, because then that gives us something about uncertainty in the estimate. So for example, if I know, let's say beta hat was a scalar, if I know the distribution, I in particular know the mean and the variance. So the mean tells me something about the bias, whether I'm gonna, on average, be correct. And the variance tells me something about how uncertain the estimate is. And this is very useful. I would say maybe the main job of statisticians is to do these things. So, so some of the basic properties we can derive, for example, the mean and the variance, or the mean and the covariance matrix, we can derive under that E1 condition, if you recall, which doesn't require any distributional assumption. And some of them requires the E2, which is the Gaussianity, or having normal distribution assumption. So okay, so the only thing that we need at this point is these ideas that so the expectation of y, if you go back, is just x beta, because we assume that the expectation of noise is 0. So our assumption was that the expectation of the epsilon is 0, and the covariance of sigma epsilon is sigma squared. And this leads to the fact that the covariance of y is sigma squared I identity. Okay, so these are the two pieces of information that we start with. And this x beta we're going to call mu, which is the true mean vector, not to be confused with mu hat, which is the vector of fitted values. So this information implies that the expectation of y is mu. This is just mu. And covariance of y is sigma squared identity. Okay. So now we have a bunch of questions. For example, I could ask, so, sorry, this. So I could ask, for example, what are the properties? This is strange, sorry. Do this. Okay, so this worked out. So, for example, what is the distribution? what is the distribution of beta hat, which is x transpose x inverse x transpose y. So what I can ask is, for example, what is the expectation of beta hat? The first thing. So given this information that the expectation of y is this, and the covariance of y is that, what is the expectation of beta hat? How should we compute this? So we don't have many people in the class left. So I can call on one of you if you don't want to volunteer. Or you maybe want to volunteer.
Would you just plug in x beta for y, and then you can like cancel out some of the terms there because the x transpose and the x would go to 1.
Okay, so I'm gonna plug it in here. X transpose beta plus epsilon. Yeah, so that's the definition.
Right.
And then I get x transpose x beta plus x transpose x inverse x transpose epsilon, right? Yeah. And so what cancels out?
Like
This.
isn't x transpose? Yeah, both of those.
Yeah, so those are, this is the inverse, yes, so this would be identity. So what I would get is beta plus x transpose x inverse x transpose epsilon. Okay, so this is good. So now how do we compute the expectation? This is a new expression for beta hat, which is quite nice. So how do we conclude? So this part is still random. So when you take the expectation, there should be no randomness. So what is this? So
Would you like do out the x transpose x to -1, and then one of those terms should cancel with the x transpose next to it, or maybe not?
no, you can't like do anything to this piece. So you can't like take x transpose x out because they're not square. So this cannot be broken up. So there should be some other strategy. So what properties or expectations do you know about? So let's say I have expectation of the sum here. So I'm just replacing beta hat with this expression. So can I move the expression inside the summation? Can I do expectation of beta plus expectation of this other term? Is that doable? Is it valid? Yes. So why? In the chat, Anna says yes.
Just like the properties of expectation, you can distribute it like when it's addition inside the parentheses.
Yes. So this is an example of a linearity. Like the property is called linearity expectation. So you can pass it through additions and scalar multiplications. So what is the expectation of beta?
Is it unbiased? Is it just beta?
It is unbiased, but why? So we're trying to prove that it's unbiased. We don't know yet.
Oh, okay.
So if this is true, this is beta. But why?
Because the expectation of error is 0, so the second term will go away.
So we haven't talked about the second term yet. I'm talking
Okay.
about the first term. So why the first term, the expectation, I can write it as beta. What was our assumptions about beta?
That it was random. That's what we had before. I don't know if that's what you're looking for.
That was the opposite of what we had before. So we had that beta is non-random.
Oh, non-random, yeah.
Yes. So that's true. It's still true. So beta is non-random. So can you justify this step then?
Doesn't that just mean like its expectation will be itself without any?
Yes.
Like
So
random.
exactly, because this is non-random, it's deterministic. The expectation of a deterministic object is such itself. So it's like vacuous. So that's why it's beta. Now, how about this one, the second term?
I think you can pull the x, that whole x part out, right?
Great. So this part comes, this is a matrix. This is like, let me do this. It's like writing this as, if you want, we call this A. We have expectation of A times epsilon. A is non-random. So this would be equal to A expectation of epsilon because A is non-random. So X is not random. So now the expectation of this is 0. So this whole thing would be 0. Right, so that's how you do it. So Y, we can take the A out, any property. So Y, expectation of A epsilon is equal to A expectation of epsilon. Does this look familiar?
Yeah, isn't that like lemma 1 or something?
Yeah, something like that, exactly. So lemma 1. This is one of the lemmas that we had. So this is another instance of linearity of expectation. The same property in matrix form. So conclusion. So conclude that expectation of beta hat is beta. And so this is saying that says that beta hat is unbiased. So that we actually have proven this statement. Okay, so we don't need to use it, we just prove it. Okay, so this was an interesting example. If you go through the lecture notes, I do it a little bit differently. So instead of simplifying in terms of epsilon, you can just work with this expression and then move the expectation inside past this to the expectation of y. So the other approach 2, which I encourage you to go through, you can say that beta hat is in fact A times y. A is the same matrix, so A is X transpose X inverse X transpose Y. And now I can say that expectation of beta hat is A expectation of Y by the same idea. And this we have shown that this is X beta. This is just from our previous discussions. And so this turns out to be A X beta. And then you can show that this is actually identity. So this is another more direct approach, but this is also an interesting approach. Sometimes it's helpful to simplify first. So if you first simplify the expression a little bit. And so that was also a nice approach. So approach 1. And this is approach 2. Okay. Questions? So now how about How about the covariance of beta hat? How can we compute the covariance of beta hat? Anyone? Can we use this, for example, expression? We can also use this, but it's easier to use the other one. So what happens if I write this as covariance of AY? Does this ring a bell? There's any?
Yeah, you could do like a squared times the variance of y.
A squared times the variance.
Oh yeah, yeah.
Okay. Is there any objection to this? Is this good? So this is a vector, right? So what does a variance of y here means? So this would be okay if a and y were scalars, right? But we need a little bit more care here.
Though like a variance of y like a transpose, is it that instead?
It's close.
Okay. Or the other, yeah, something like that.
Yes, but still, this is ambiguous. What does it mean? What do you mean by the variance of y?
Wait, shouldn't
it
it
a
be covariance of y?
Okay, now
Yeah.
we're good. So this should be covariance of y, which plays the role of the variance for a vector. So now this is an n by n matrix. So things work out. This is n by n, and a you can verify that this is p plus 1 by n, and this would be n by p plus 1, and this is p plus 1 by p plus 1 because that's the dimensions of the beta. So everything works out here. So what is the covariance of y now?
It's like sigma squared times I.
Yes, sigma squared times I. So how can I simplify this?
I don't
Okay.
know.
So this scalar I can put out. So a scalar just moves around freely. I get A times identity times A transpose. Can you get rid of the identity somehow?
Yeah, and then a times a transpose will just be identity.
Okay, not so fast. So you wanted to say that this is identity.
Yeah.
It would be great if that's true,
Oh, okay.
but this is debatable. So let's try to figure this out. Up to that point is fine. This one last step we need to verify. So A transpose. This is X transpose X inverse X transpose. And then how do I take the transpose of this? I want the A transpose here. Do you remember how to take the transpose of a product?
You apply the transpose to all the terms, but you switch the order.
Great. So what would that be in this case? So
just
yeah. So what terms should we be looking at here?
We can do the one in the parentheses and then x so that it becomes just x, regular x times the thing in the parentheses transpose, and then you can do that process again for inside the transpose.
Like that. So the transpose of this, which is this, and then transpose of this, and then order switch. So this is correct. Then what? What was the next one? Do the.
I think you could bring like switch the inverse and the transpose.
Yes, we could do that. So we could say that this is equal to X transpose X transpose inverse. That's also valid. then? So what is the transpose of this?
I think it's the same thing, right?
Yeah, so if you do this operation, again, you can do transpose, switch the orders, and so you get this transpose times this transpose, which is just going to be the same thing. So this is a symmetric matrix, so this is going to be equal to its transpose. And after a while, you realize that you didn't need to do this operation, so this whole thing is symmetric, its inverse is symmetric, and so its transpose is going to be itself. So you can just written this as, but this is good to do as an exercise. So this turns out to be X, and the other one transposes just itself because it's a symmetric matrix. And this is true because this is a gram matrix. Gram matrices are symmetric, and the inverse of a symmetric matrix is symmetric. Okay, so this is not what I meant. So I have to plug in. So you get X transpose, X inverse, X transpose, and then the inverse, the transpose of that, which is X, and then X transpose, X inverse. So that's A transpose. Okay, that's A. So now what is the final step here?
You can cancel the, like, two of the, like, you can just choose one inverse to cancel it into I.
Great, so I can, for example, choose, yeah, so in matrix multiplication, you can put parentheses anywhere you want. So I can just think of this as add these parentheses here. So I have this object inverse and then the same object, so I can cancel these two. So this would be just the identity. And I'm left with just X transpose X inverse. So I'm having like one matrix inverse and the same matrix and then inverse of the same matrix. So one of them cancels out. So this turns out to be a little bit more complicated than what we hoped. This is going to be this gram matrix inverse, basically. Okay, so if it was identity, everything would be simple. But unfortunately for us, this is not going to be identity. So there's going to be some non-trivial covariance matrix. So the beta hat, so this X transpose X in general is not identity. It's the gram matrix of the columns. It's going to be identity if and only if the columns are orthogonal. That's what we talked about. The gram matrix identity if and only if the columns are orthonormal. Actually, columns are orthonormal, which means that they're orthogonal and then they have unit norms. In all other cases, this is going to be non-identity, and so you'd have non-trivial covariances between beta hat I and beta hat j. So the entries of beta will be correlated, and this complicates things in linear regression. Okay, so but this is a good place to stop. Since we're out of time, I'm not gonna spend too much time here. Just go over this for yourself and in the lecture videos, and we can come back next time if you have questions. Let me know. But this is a very good exercise for you to go through and try to drive these for yourselves. It's very important for us later on, and you have all the information. So, okay, sounds good. Okay, if you have no questions, we can stop here.
Thank you, Professor.